Hello! We are very pleased to welcome you on board this massive open-line course on the B-formal method. For this training, our objectives are to demystify the B-formal method by showing how to use it practically and to bring each learner to a level of competence and confidence, enabling him to develop non-trivial software with B. The course is divided in 4 chapters. A chapter on basics, which provides an overview of the B method and its key concepts. A chapter on modeling, with the abstract machine, the mathematical language to express properties, the architectural clauses to structure the models, and the refinement mechanism. A chapter on implementing, with the decomposition-based development, the concrete data and algorithms, the loops that terminate, and the code generation. A chapter on proving, with the understanding of proof obligations and how to complete a proof. At the heart of the formal method is the notion of specification. A specification is a model of a system that contains a description of its expected behavior. 2 issues arise: how to enforce at the specification level the expected behavior, and how to obtain from a specification an implementation with the same behavior. Or given an implementation, how can it be guaranteed that it has the same behavior as a specification? The different families of formal methods cover a wide range of approaches to these 2 questions. This variety encompasses the study of specification by animation, by transformation, or by proving properties. Implementations may be derived from specification, guaranteed to be correct with respect to them, either by construction or by verification, meaning by presenting a formal proof. An existing taxonomy distinguishes formally designed software on one end, when formal methodologies and tools are applied in the horizontal fashion, and formal development on the other end, when the correct by construction approach in the vertical application, and when formal proof facilities are also provided in addition to the generation of code. 2 features greatly help the engineer to complete his duty. First, the formal nature of the specification language employed forces one to reason about and to understand all the fine details of the specified system, and thus clarify potential hidden ambiguities. Second, the possibility to animate or even execute a specification, and thus to directly observe its behavior if an implementation of the underlying mathematical formalism exists. Such a functionality allows for the system to be prototyped. A straightforward advantage of having a prototype is that it is in general simpler to deploy than the system itself. A prototype makes possible the validation of a system without actually implementing it. Regarding specification style, there are 2 main approaches to formal specification. First, the behavior of the model system can be expressed by focusing on its operations or actions that can be performed. In this view, the crucial element is a clear definition of the modifications or changes performed by each operation on the internal state of the model systems. Such specification languages are referred to as state-based or model-based specification languages. The behavior of the target system can instead be expressed by focusing on the manipulated data, how they evolve, or the way in which they are related. This class of specifications include algebraic specification. We may cite the language Lotus. We can also mention the declarative modeling. In declarative models, the focus is on what the solution is. It includes logic-based languages like Prolog, functional languages like OCaml and Coq, rewriting languages like Elan, and languages for defining formal semantics. So to sum up, with B, we have a formal development that is vertical, correct by construction. The behavior of the model software can be expressed by focusing on its operation, and it's referred to as a state-based or model-based specification language. Several myths on formal methods have to be known. Formal methods are usually only applied when necessary, meaning when something has to be demonstrated. More traditional means are used in all the other cases. Formal methods are used on applications containing several hundreds of thousands lines of code. Formal methods may also be applied to systems at large and used to validate, for example, procedures, business rules, or security policies. Automotive, railway, and aeronautic standards strongly recommend to use formal methods for the highest safety critical levels. The microelectronics common criteria standards require them. Formal methods may be applied in every critical system that could be economic critical, quality critical, in fact in any domain where a bad product may have a major impact on the reputation of the company. The software executes on hardware that may fail and coexist with other software that may disrupt its behavior. Perfect software is an illusion, as its environment has to be considered, so there is still room for testing, especially at integration and validation level. Formal methods are applied at system level as well. Formal methods may be applied at system level, at software level, for the design or for verification purpose. Many different approaches, more or less invasive, that have different impact on the existing development cycle. Formal methods require people able to model and to handle abstraction. Of course, mathematicians fit with this profile, but also a number of regular engineers. Formal methods are applied every day by a wide range of professionals using industry-strength development environments and dedicated engineering advanced support. If you consider the complete product cycle including maintenance, the costs are usually lower because the final products are likely to be default-free. When the formal development cycle is set up, the specification phase is usually longer, but the overall development process is speed up because errors are detected early and model reuse nicely applies to a product line. Many formal method tools are certified or qualified and referred to in standards. The formal method tool vendors provide industrial support, while the related scientific community ensures a continuous research. That's all for today, guys. I hope you enjoyed the video. See you soon in the next one, and remember, formal is fun.